first of all, we are discussing what is the laser ablation and how the laser interact with the material. So we are discussing laser spectroscopy, or this can be shown as this may be called as a laser ablation, or another name is laser induced breakdown spectroscopy. Laser induced breakdown spectroscopy, or laser matter interaction. So this is the basic fundamental physics what we have discussed. So we are saying that the laser spectroscopy, it means it is clear that we are discussing with the light. And you know that laser stands for light amplification by stimulated emission of radiation. It means this laser light is simply laser light, which we call it as a coherent light, coherent or monochromatic light. ठीक है, मोनोक्रोमेटिक का मतलब है कि दिस इज द सिंगल कलर लाइट, सिंगल वेवलेंथ लाइट. So it means its wavelength is a single wavelength, lambda is fixed. Coherent means the phase difference between two waves is a zero. It means the phase of both waves is the same, which we say that if the one wave is starting from the zero, the second wave will also start from zero. So it means when they superimpose, they will interfere constructively. So the interference between two waves must be constructive interference. So we may call it as a coherent. If it is not coherent, the phase difference is, let's say, 180 degree, then the trough of one wave may cancel out the crest of other wave. As a resultant, we will get a destructive interference, no light. So as a resultant, for the laser, the main thing is the light is a coherent, and the second thing is it is the monochromate. In this study, we will use a pulsed laser. There are different type of lasers. We call it as number one is the pulse laser, and number second is the CW laser. CW laser is the continuous wave laser. It is the continuous wave laser. So this pulse laser is in the form of the pulses. These are the pulses. This is in the form of the pulses. But actually, this is the square pulse. But the pulse of the laser is the Gaussian pulse. So actually, the pulse which we will get is in the form of this pulse, this pulse, this pulse, this pulse, this pulse. So the laser is in the form of the pulses. This is called the pulsating laser. The light emitted out from the laser in the form of the pulses. So this is known as a pulsating laser. So this is the pulsating laser. Light is emitted out in the form of the pulse. This duration of one pulse is known as pulse duration. This is called the pulse duration, or this is called delta lambda, which is the this is the full width at half maximum, full width at half maximum. This is known as a maximum. This is the maximum value, or which we call it as the amplitude of the wave. Clear? So this is called the amplitude of the wave. Half of the amplitude is this. This is the half. So here it is a full width at half maximum. Delta lambda 1 by 2 is known as the full width at half maximum. The light which are emitted out from the laser is in the form of the pulses, and we call it as a pulsating laser. How many pulses are emitted out per second, which we call it as a repetition rate. Repetition rate is the number of pulses emitted out per second, which we call it as a repetition rate. So here repetition rate repetition rate is the number of pulses emitted out per second. It means the repetition rate is defined as the number of pulses emitted out per second is known as repetition rate. Which means how many waves are emitted out per second, and here this is called the pulse duration. If we say that this is the light which is emitted in the form of the pulses, here these are the pulses which are emitted out from the source. Clear? So here if we say that here this is 1 2 3 4 5 6 7 up to let's say 10. So here 10 pulses per second. It means if the laser emitted out 10 pulses per second, which we call it as its repetition rate. The repetition rate here in this particular case is a 10 pulses or 7 pulses per second, which we call it as a repetition rate. If the laser emits out the pulses per second, is its repetition rate. If the laser emits 5 pulses per second, so the repetition rate is 5 repetition rate. Here, this is the duration of the pulse. This is called, which we call it as a pulse duration. Clear? This is called the pulse duration. It means the pulse is for such a duration, which we call it as a pulse duration. Clear? If we say just this pulse duration may be any time, maybe 4 nanosecond, maybe 5 nanosecond. This pulse duration, this varies from laser to laser. There are different types of laser. Clear? Some lasers are known as a solid state laser, and this is one of the example of the solid state laser, or we call it as a, let's say, Nd:YAG. This is the compound material which we call it as a Nd:YAG, neodymium yttrium aluminum garnet. So this is one of the laser, and this laser emits out the light in the form of the pulses, and we call it as a pulsating laser. Clear? The duration of the pulse may be in the nanosecond, maybe in the picosecond, maybe in the femtosecond. Pulse duration may have different times, durations, nanosecond, picosecond. This pulse duration may be femtosecond. So here, this nanosecond laser is known as ns. This is the symbol, and its duration is 10 raised power minus 9 seconds. And this picosecond is called ps. It is 10 raised power minus 12 seconds. And this femtosecond, which we call it as a fs, this may be equal to 10 raised power minus 15 seconds. So this indicates the duration of the pulses, and we call it as a pulse duration. This is the duration of this pulse, and we call this as the pulse duration. This pulse duration may be nanosecond, maybe picosecond, maybe femtosecond. Clear? So it means when this pulse hits a material, this indicates the duration of the pulse, how much duration this pulse can interact with the material, to ablate the material, to evaporate the material. Now, depending upon the energy of this pulse. Clear? So, as a resultant, you know that the energy is related to the wavelength. So, lambda is the wavelength of the laser, and this lambda or energy, you know that E is equal to hc over lambda, and lambda is equal to hc over E. So E is the energy and lambda is the wavelength. It means now the pulses which are emitted out from the laser is in the packets of energy. This E is the energy of each packet. E is the energy of each packet, and lambda is the wavelength of each packet. For example, let's say what we have used here in our experimentation, we have used three types of wavelengths. Clear? One is in the range of IR, other is in the range of visible, and third one is in the range of the UV laser. So what are the wavelengths and how we can find out the energy of each photon, or which is the energy per packet. So here in this case, you can find out the energy. For example, we have used in our experimentations wavelength lambda is equal to 1064 nanometer. This is the first wavelength which we have used. And from this wavelength, this is the wavelength in nanometer, you can convert it into the angstrom. Clear? So this wavelength you can find out means this is the wavelength of the light which is coming out from the source, from the laser source. And this light is to be interact with the material. These are laser matter interaction, laser induced electron spectroscopy, laser spectroscopy. These all depending upon the properties of the laser. So in the first step, we are discussing the properties of the laser here. So if the lambda is equal to 1064 nanometer, so the energy E can be find out. E is equal to Hc over lambda. The value of Hc is equal to 1240 electron volt into nanometer divided by lambda. So the E, this is the value 1240 is the value of H into C in terms of electron volt into nanometer. You can convert it into easily. Hc, you know that H is equal to 6.67 into 10 raised power minus 34 joule into second, and C is equal to 3 into 10 raised power 8 meter per second. So if you multiply both, you will get joule second, second cancel, joule into meter. This joule can be converted into the electron volt by dividing 1.6 into 10 raised power minus 90. If you divide it, please close your video. So this is 1 point, if you divide it into 1.6 into 10 raised power minus 19. So as a resultant, this now joule becomes an electron volt. And if this meter is divided by 10 raised to power 9, this becomes a now nanometer. So as a resultant, you will get a value 1240, which is equal to electron volt into nanometer. So here E is equal to Hc over lambda, which is equal to 1240 electron volt into nanometer divided by lambda, which is equal to 1064 nanometer. So nanometer cancel. If you divide 1240 with 1064, you will get the value in the electron volts. So this will be equal to 1 point something. Clear? So if you divide this with the, let's say we are using calculator here. So 1240 divided by 1064 is equal to E is equal to 1.165 electron volt. So this is the energy of the photon. This is the energy per photon. This is the energy of the single photon whose wavelength is lambda 1064. Similarly, you can find out the energy of the other photons. For example, second is the lambda is equal to 532 nanometer, and the third wavelength which we have used, lambda is equal to 355 nanometer. So here the energy this belongs to, this is called the IR. This energy is in the range of IR laser, infrared laser. And this lambda 532 is in the range of visible. So you can find out easily its energy, which is equal to, let's say, let's discuss it. So 1240 divided by 532, this is equal to 2.33 electron volt, and this is equal to energy is equal to, here 1240 divided by 355, this gives you a 3.49293 electron volts. So this is the energy for the visible light. This is for visible, and this is for UV, ultraviolet. So we have three types of laser available: IR, UV, and visible. So, which laser is to be fired on the material to ablate the material depending upon the nature of the experimentation. What is your experiment? What is your requirement? So the choice of the wavelength is totally depending upon the choice of the experimental conditions. So here it means when this laser hits the target, as a resultant it evaporates the target. Clear? So what this interaction of the laser metal interaction depending upon the properties of the laser and depending upon the properties of the material. How? Let us discuss it. So now here, so now here we are discussing laser metal interaction. So now in the laser metal interaction, simply this is the pulse, laser pulse. This pulse is in the form of the Gaussian pulse. This is the pulse, and this pulse when it strikes with the material, this is the material, and this pulse strikes with the material. As a resultant, it evaporates the material. So material will be evaporated if the energy of the pulse is greater than the threshold value of the vaporization of the material. If the energy is less than the threshold, means minimum energy needed to vaporize the material, then this pulse will never vaporize the material. So here in this case, if we look here, this pulses, this height of the pulse depending upon its intensity. For example, this is the pulse. We have another pulse. For example, let's say this is the same pulse whose intensity is this. If we look into these two pulses here, the magnitude of this pulse is this, the amplitude of this pulse is this. The amplitude is different here. The amplitude of the pulse is known as the number of photons emitted out per unit area, per unit time. And the energy of each photon is same because the wavelength of each photon is same. Wavelength is same. So only the amplitude increases. The amplitude shows the number of photons, or we call it as the intensity. This means the number of photons emitted out per unit area per unit time. So this is known as the intensity. It means if we say that the energy here which we have discussed, the energy of light is, let's say this energy is 1.16, let's say IR, 1.16 electron volt. So here in this case, for example, a single photon cannot produce the ablation, cannot vaporize the material. It means how many photons is striking over here to produce a ablation. If we say that if we multiply with 1000, it means if 1000 photons simultaneously hits the material, as a resultant it can evaporate the material. Clear? So from the pulse, from the intensity, you can find out the number of the photons. It means you have a meter, or that meter measures the intensity of light. It means if you fire the pulse on the meter scalar will give you the its energy. Clear? So this is not an energy, this is actually the intensity. Because energy, you know that the wavelength is known, energy per photon is known. So from the meter, from the energy meter, you can measure the how many photons are coming out per second. Because you know that in the laser principle, in simply, it is the stimulate light emitted by stimulated emission of radiation. Light is coming in this direction and then returning back and then coming. So as a resultant, inside the cavity of the laser, this is the multiplication. It means the photons are multiplied, and if they have a path here, they emitted out from the cavity of the laser. So as a resultant, how many photons are committed out, this depending upon the time duration. So how much time is needed to open the shutter? It means, or the shutter is open for how much time? So that depends the energy of the pulse, the intensity of the pulse, depending upon the shutter time. Okay, in the pulsating laser. So here, this its amplitude is almost double of this. So therefore, the number of photons of this pulse is the double of this. Intensity is all, but the frequency or energy per photon is the same. So therefore, here when it hits the material, as a resultant, it ablates the material. So in this laser matter interaction, the characteristics of this ablation depending upon the laser properties, depending upon the material properties. This material may be the liquid, this material may be the solid, this material may be the liquid solid, and it may be in the form of the gases. So in any form, in any phase, material can be interact with the laser light. So here, if we look into this, the laser properties, so here in this laser properties, number one is the wavelength. So here number one is the wavelength, and number two, pulse duration, and number three, intensity of the pulse, and number four is repetition rate, or number four is not necessary. So here these are the basic properties of the laser which is to be considered before the interaction or before the laser matter interaction. So here it means the ablation of the material depending upon these properties. So how much material is ablated or vaporized during the laser matter interaction? So this is totally depending upon the nature of the wavelength. This is totally depending upon the pulse duration, and this is totally depending upon the intensity. If we increase the intensity, as a resultant, the evaporation of the material will also increase. If you increase the pulse duration, the material which is emitted out will be so hot and dense. It emit out more light as compared to the cold plasma. And the emitted material or evaporated material is in the form of the plasma, and which is the ionic state of the material. Material may be gases, material may be liquid, material may be solid. The third is in the wavelength. If we increase the wavelength, the coupling of the material will decrease. Because you know that when the light strikes, this is the light, this is the photon. When the photon strikes on the surface, the coupling of the photon with the surface is totally depending upon the wavelength of the photon, or it depends upon the critical density of the material. So if the wavelength is large, the most of the light is reflected back. If the wavelength is small, the maximum light can penetrate into the material. So it means the wavelength plays an important role for the laser ablation, for the laser material interaction. It means the maximum light will be utilized to ablate the material if the wavelength is small. It means the evaporation produced by the UV laser is much dominant as compared to the evaporation produced by the IR laser. Because in the IR laser the wavelength is large and in the UV laser the wavelength is small. So large wavelength produce a small evaporation and small wavelength produce a large evaporation because the small wavelength has a large energy per photon. So as a resultant, the coupling with the material will be increased. The reflection of the light from the surface will decrease. So as a resultant, more energy will be utilized to evaporate the material. Okay, so here these are the properties of the material. So it means the characterization of the laser matter interaction depending upon the laser properties, and the second depending upon the material properties. And here material properties are depending upon the material properties. Now what are the material properties? The material properties are here simply number one is the thermodynamic properties. Thermodynamic properties, and in this thermodynamic properties is, what are the thermodynamic properties? It is the heat capacity, latent heat of vaporization, latent heat of vaporization or vaporization temperature,